The universe is a cosmic web, and its most powerful intersections are tearing themselves apart. Our very existence hinges on star stuff forged in these violent galactic mergers. By the end of this journey, you will understand how these collisions dictate the fate of everything, from the largest structures in space to the atoms in your body. We will uncover how invisible dark matter orchestrates the chaos and why a galaxy's brilliant blue fire can be permanently extinguished. What forgotten story does the silent, red glow of an ancient galaxy hold? This vast cosmic architecture, a delicate balance of immense gravitational forces, is far from static. The very nodes that anchor this great web are themselves in constant, slow-motion conflict. When two of these dense clusters, these galactic cities, are drawn together, their merger is one of the most violent and transformative events in the cosmos. It is not a gentle meeting but a prolonged gravitational dance that can last for billions of years, a dance that fundamentally reshapes the participants and the node they call home. The initial encounter is often a near miss, a close gravitational pass that sends shockwaves through both clusters, distorting their shapes and pulling long streams of stars and gas out into the void. But the pull is too strong to escape. They fall back toward each other, beginning a series of ever-tightening orbits. With each pass, their vast clouds of hot gas, which fill the space between the galaxies, slam together. This intergalactic medium, heated to millions of degrees, creates some of the most powerful shock waves in the universe, visible only to X-ray telescopes. These collisions ripple through the entire node, stirring up the dark matter that forms its true backbone. The individual galaxies within the clusters, meanwhile, experience this as a radical change in their environment. Their orbits are scrambled, their paths thrown into chaos. Some are flung out into the lonely filaments, while others are driven toward the chaotic center of the merging node. It is here, in this crowded, turbulent core, that galaxies themselves are forced to change. Their spiral arms are torn away, their gas reservoirs are stripped, and they are often pushed into catastrophic collisions with one another. This is the forge where the brilliant blue fire of star formation can be ignited to an incredible intensity, or, paradoxically, extinguished forever. How can such a violent collision both create and destroy a galaxy's ability to give birth to new stars? The answer lies in the delicate balance of the gas that fuels it all. That slow-motion dance of titans is governed by an unseen partner. Dark matter forms the overwhelming gravitational skeleton of every galaxy and every cluster, a hidden architecture that guides the visible universe. During a merger, this dark matter halo surrounding each galaxy does not collide in the way stars and gas do. Instead, the countless particles of dark matter simply pass through one another, an invisible, ghostly interaction. Yet their collective gravity is the true director of the chaos. It is this dark matter that first pulls the galaxies together, that orchestrates their intricate orbital dance, and that ultimately determines the final shape of the merged remnant. While the visible stars are stretched into spectacular tidal tails, and the gas clouds slam together in furious shock fronts, the dark matter halos undergo a process known as dynamical friction. They slowly merge, their gravitational influence smoothing out the violent motions, eventually settling into a new, larger halo that will host the newly formed elliptical galaxy. This invisible framework is what makes the cosmic web possible, and its transformation during a merger reconfigures the node itself. But what happens to the vibrant, star-forming gas caught in the middle of this gravitational storm? The glittering galaxy we see is merely the tip of a cosmic iceberg. The true bulk, the immense gravitational anchor, is the vast, unseen dark matter halo that dictates its every motion and ultimate destiny. This invisible substance makes up roughly 85% of all matter in the universe, forming the essential skeleton upon which the entire cosmic web is built. The distribution of this dark matter is paramount, as its gravitational wells are what first pull together the gas and dust that will become galaxies, creating the dense nodes of the web. Pioneering astronomers like Vera Rubin uncovered compelling evidence for this hidden component by studying galaxy rotation, finding that stars at the edges of galaxies moved far too quickly to be held in place by the gravity of visible matter alone. Something unseen, a deep gravitational anchor, had to be there. During a galactic merger, the most dramatic collision is not between the stars, which rarely touch, but between these immense, interpenetrating halos of dark matter. They do not crash like solid objects, but instead slosh and stream through one another in a complex gravitational dance. Advanced computer simulations reveal that the dark matter halo of a smaller galaxy can be tidally shredded, stretched into long streams, and ultimately absorbed by the larger halo, effectively redistributing the invisible mass throughout the entire node. So how does this unseen rearrangement of mass manifest in the brilliant, visible properties of the merging galaxies? This profound interplay between the invisible scaffolding and the luminous gas sets the stage for the most violent and creative process in the cosmos, the birth of new stars. This brilliant firestorm of creation is a galaxy in overdrive. Within the cosmic pressure cooker of a merger, shockwaves slam into colossal clouds of molecular gas, the raw material for stars. This violent compression triggers a chain reaction, forcing dense pockets within the clouds to collapse under their own gravity. The result is a starburst, a spectacular frenzy of star birth that can produce thousands of new suns every single year. For context, our own Milky Way galaxy forms a mere 1 or 2 new stars annually. This explosive period of creation is so intense that it can outshine the combined light of every other star in the galaxy. Much of this brilliant light is initially absorbed by the very dust clouds that spawn the new stars, only to be re-radiated as a powerful, telltale infrared glow that observatories can detect across the universe. A prime example is the Cigar Galaxy, a nearby system whose core is a raging firestorm of stellar nurseries, a condition widely believed to have been ignited by a past gravitational encounter. But this furious burst of creation cannot last. The very process that ignites the starburst also sows the seeds for its own end. All those brilliant new stars, especially the most massive and short-lived ones, flood their surroundings with intense radiation and powerful stellar winds. This relentless output acts like a cosmic hurricane, violently sweeping away the remaining gas and dust, the very fuel for future generations of stars. So, how can a collision that triggers such a firestorm of creation also lead to a galaxy's permanent retirement from star formation? This brilliant firestorm of creation, however, often awakens a far more formidable power sleeping at the galaxy's very heart. A supermassive black hole, typically a silent and dormant giant, is stirred by the chaotic inflows of gas from the merger. As vast rivers of fuel are funneled toward the galactic center, the black hole begins to feast. The material does not fall in directly, but spirals into an intensely hot, glowing disk of accretion, transforming the core into a brilliant, active galactic nucleus, outshining the entire galaxy for millions of years. This is not a gentle awakening. The infalling gas heats to incredible temperatures, emitting a ferocious blast of radiation across the entire electromagnetic spectrum, from X-rays to radio waves. In some of the most extreme cases, this process can also launch twin jets of charged particles, shooting out for thousands of light years at nearly the speed of light. The galaxy known as NGC 6240 presents a stunning snapshot of this process in motion, where two separate black holes from the merging galaxies now orbit each other in a tight dance, destined to eventually collide and merge themselves in a titanic release of gravitational waves. Astronomer Andrea Ghez, awarded a Nobel Prize for her pioneering work on the black hole at our own galaxy's center, has emphasized that these objects are not merely destructive. They are integral to galaxy evolution. But how does this immense energy output from the core influence the wider cosmic node? The answer lies in a powerful cosmic feedback mechanism. The intense radiation and winds from the active black hole can blast through the surrounding galaxy, violently heating and dispersing the remaining reservoirs of cold gas. This effectively shuts down the very star formation that the merger initially ignited, putting the galaxy on a path to a quiet, red retirement. This feedback is a key regulator, a balancing act of cosmic proportions, capable of both fostering and then decisively quenching a galaxy's future growth. This gravitational tango fundamentally rewrites the rules of motion within the galaxy. The orderly, circular orbits that once defined a tranquil spiral disk are thrown into a state of pure chaos, as gravitational forces pull from multiple, shifting centers rather than a single, stable core. Stars are sent on wild, unpredictable paths, slingshotting through the turbulent node. This chaotic churning acts like a cosmic blender, efficiently erasing the delicate disk structure of spiral galaxies. The entire system, seeking a new balance, undergoes a profound transformation known as violent relaxation. It is not a gentle process, but a rapid and radical redistribution of energy that scatters stars into a new, random configuration. Advanced computer simulations, like those from the IllustrisTNG project, provide a stunning visual of this evolution, showing how the once distinct populations of stars from the two progenitor galaxies become thoroughly mixed into a featureless, swelling sphere. We see this dramatic process captured in action with systems like the well-studied MICE galaxies, where colossal tidal forces have pulled immense streams of stars far out into the emptiness between galaxies. But what becomes of this stellar debris ejected into the void? These exiled stars do not simply vanish. They instead become permanent residents of the node's extended halo, a faint but vast cloud of ancient suns that enriches the intracluster environment. This scattered population contributes to a diffuse light that permeates the entire cluster, a ghostly echo of the colossal merger that created it. The chaos of a galactic merger extends far beyond the two central players. Think of a flock of birds suddenly caught in the turbulent wake of two colliding airliners. In a similar, vastly grander fashion, the smaller satellite galaxies orbiting the primary pair are subjected to extreme and unpredictable gravitational forces. These dwarf galaxies, often just a fraction of the size of their hosts, can be completely torn apart, their stars stripped away and added to the main galaxy's growing halo. Others are not shredded but are instead flung out onto entirely new trajectories, becoming gravitational orphans ejected into the lonely depths of the node. The halos of large galaxies like our own Milky Way are littered with the stellar debris of such cannibalized satellites, a cosmic archaeology record written in starlight. Astronomer Beth Willman and others have dedicated their research to mapping these faint streams, using them to trace the violent history of our galactic neighborhood. A prime example is unfolding right now, as the Sagittarius dwarf spheroidal galaxy is slowly being stretched and absorbed by the Milky Way in a preview of this very process. This steady accretion of smaller systems is a primary method by which the most massive nodes grow, not just in their visible stellar halos but in their total invisible mass. This hierarchical buildup, where large structures form through the successive merging of smaller ones, is a cornerstone of our modern cosmological model. It reveals a universe built not in a single instant, but through a prolonged and ongoing history of assembly and destruction, forever shaping the destiny of the cosmic web itself. The universe builds itself from the ground up. The grandest structures we see, the immense galaxy clusters anchoring the cosmic web, were not born that way. They are the products of a relentless, bottom-up assembly process called hierarchical clustering. This foundational idea in our standard model of cosmology tells a story of small beginnings, where the first tiny dark matter halos, emerging from the primordial soup of the Big Bang, began to attract gas, forming the very first faint galaxies. Over billions of years, gravity orchestrated a slow-motion dance of attraction and union. These small galaxies merged to form larger ones, which in turn collided to build the giant ellipticals and the vast clusters that dominate the nodes we observe today. Each major merger we have been exploring is a pivotal chapter in this story, a dramatic leap up the cosmic ladder that significantly boosts the mass and gravitational pull of the resulting node. Pioneering cosmologists like Simon White used some of the first sophisticated computer simulations to visualize this process, showing how dark matter halos merge and grow like cosmic snowballs, accumulating mass over eons. The evidence for this history is not just theoretical, it is written in the stars themselves. When we look at a massive elliptical galaxy at the heart of a node, we are seeing a fossil record. Detailed studies of its starlight reveal populations of ancient suns with distinct chemical signatures and motions, stars that clearly originated in different, smaller progenitor galaxies that were violently stirred together long ago. The very chemistry of these stars acts as a cosmic DNA, tracing their lineage back to separate systems. So, what other observable signatures does this hierarchical history leave behind? The answer lies in the motions of the stars and the overall shape of the galaxy, clues that allow astronomers to piece together the entire merger history of the universe, one galactic fossil at a time. These galactic collisions are more than just a rearrangement of stars. They are cosmic crucibles where the very elements of life are forged and scattered. The interstellar medium, the thin soup of gas and dust between the stars, becomes a turbulent chemical laboratory during a merger. Gas from two distinct galaxies, each with its own unique chemical history, is violently stirred together. This mixing, combined with the ferocious burst of new star formation, triggers a rapid and dramatic increase in metallicity, a term astronomers use for the abundance of all elements heavier than helium. To understand the significance of this, we can look to the work of researchers like Anna Frebel, who studies the most ancient stars in our galaxy. These primordial suns are incredibly metal-poor, preserving the pristine conditions of the early cosmos. They stand in stark contrast to the metal-rich stars born in the chaotic aftermath of later mergers, stars like our own Sun, which carries the chemical legacy of countless ancestral supernovae. Within the firestorm of a merging node, the cycle of creation and destruction accelerates exponentially. The massive stars born in the starburst live for only a few million years before ending their lives in colossal supernova explosions. Each detonation is a stellar factory, fusing lighter elements into heavier ones and then blasting them out into the surrounding space, enriching the galactic environment with newly forged oxygen, silicon, and iron. We can see this process in action by studying ultra-luminous infrared galaxies like ARP 220. spectroscopic observations of such systems reveal intensely enhanced emission lines from a variety of metals, a direct signature of this ongoing chemical pollution. This enrichment fundamentally alters the future of the entire node. The gas clouds that will one day collapse to form new stars and planets are now seeded with a richer cocktail of heavy elements. This influences the types of stars that can form, the efficiency of planet formation, and even the chemical building blocks available for the emergence of life itself. How does this continual cycle of stellar death and rebirth, supercharged by mergers, shape the long-term evolution of the galactic ecosystem? That graceful pinwheel of stars, a delicate spiral galaxy, is a structure of exquisite balance. Its stars orbit in a coordinated, circular dance, a testament to a quiet and orderly history. But this balance is fragile, and a major galactic collision shatters it completely. The gravitational forces at play during a merger are chaotic, pulling from multiple directions at once. These forces act as gravitational torques, violently transferring the energy of orderly rotation outward, scattering it away. The stars themselves are thrown from their circular paths onto random, chaotic orbits. They no longer move as a synchronized disk, but instead swarm in every direction like a stirred beehive. The pioneering work of astronomers Allar and Jory Toomer, using some of the first detailed computer simulations, vividly illustrated this process. They showed how the beautiful spiral arms are not just distorted but are utterly erased, their structure lost forever to this stellar scrambling. The galaxy, seeking a new equilibrium, puffs up into a smooth, round or oval shape, a featureless spheroid. This transformation is one of the most profound in the cosmos, turning a vibrant, star-forming spiral into a quiescent elliptical galaxy. But what seals this fate, preventing the galaxy from ever reforming its disk? The answer lies in the gas. The same torques that randomize the stars also drive the galaxy's reservoir of cold gas violently inward, fueling the central starburst and feeding the supermassive black hole. This process is so efficient that it drains the entire system of the raw material needed not only for future stars but also to settle back into a new, rotating disk. The end product is often what astronomers call a red and dead galaxy, its blue, short-lived stars long gone, leaving behind a quiet population of older, redder stars. We see the ultimate results of this process in the hearts of dense clusters like the Coma cluster, where giant elliptical galaxies dominate the scene. So, what determines the final outcome of this cosmic reshaping? The initial conditions of the collision are everything. If the merging galaxies were already gas-poor, or if their collision was a direct, head-on impact, the transformation into a pure spheroid is almost guaranteed. However, if a significant reservoir of gas survives the turmoil, or if the merger is more of a glancing blow, there remains a chance for a new disk to eventually reform, offering a glimpse of order reborn from chaos. These dense, ancient stellar swarms are not merely passive spectators to galactic collisions. A galaxy's system of globular clusters, those shimmering balls of hundreds of thousands of ancient stars, becomes a key witness and a participant in the violent reshaping of a node. They act as a fossil record, a cosmic archaeology site that preserves the history of the merger long after the event itself has faded from view. Each cluster is a time capsule, holding clues to its own origin. During the immense turbulence of a merger, several dramatic fates await these stellar systems. Some are violently stripped from their original host galaxy, becoming gravitational prizes for the larger galaxy that emerges from the collision. This capture process can explain why some massive elliptical galaxies are surrounded by thousands of these clusters, a population far richer than any single spiral galaxy could have produced on its own. The elliptical galaxy NGC 1316 is a textbook example, its halo teeming with a complex and abundant system of globular clusters that strongly suggests a past built from multiple mergers. But the story is not only one of capture and theft. The merger itself can forge entirely new generations of clusters. In the intense pressure of colliding gas clouds within the starburst regions, conditions can become so extreme that they mimic the early universe, triggering the birth of massive, young globular clusters. These newly formed swarms are brilliant and blue, standing in stark contrast to the ancient, redder clusters that were inherited from the progenitor galaxies. This creates a mixed population, a layered history written in starlight. Astronomer Duncan Forbes has dedicated his research to reading this history, using the properties of these clusters to piece together the timeline of galactic assembly. Yet the merger is also a destructive force. The process of dynamical friction, the same drag that causes the dark matter halos to merge, can also spell the end for many globular clusters. As they orbit through the dense, chaotic core of the merging galaxies, they experience a gravitational drag that saps their orbital energy. This can cause them to spiral inward, sinking toward the galactic center where they are vulnerable to being torn apart by the immense tidal forces of the central supermassive black hole or by collisions with other clusters. So how do we decode this complex fossil record? The key lies in the clusters themselves. Their colors reveal their approximate ages, with redder hues typically indicating older, more metal-rich stars. Their chemical metallicity tells us about the environment in which they formed, whether it was a pristine, early universe or a gas cloud already polluted by earlier generations of stars. And their spatial distribution maps the gravitational history of the entire galaxy, showing us where clusters were captured, where they were born, and where they were ultimately destroyed. By reading this detailed archive, we can look at a seemingly quiet red galaxy and uncover the dramatic story of its violent birth. That brilliant blue fire of star formation requires a constant supply of cold, dense gas. But a galaxy soaring through the heart of a merging node faces a cosmic hurricane. Visualize a spiral galaxy plunging at incredible speed through the superheated plasma that fills the space between galaxies. This intracluster medium, though incredibly thin by Earth standards, acts like a relentless gale force wind. The resulting ram pressure violently strips away the galaxy's interstellar gas, the very lifeblood for new stars. It is like leaves being torn from a tree in a storm, a process that can leave a galaxy permanently starved. This crucial mechanism, first quantified by astronomers Lars Gunn and James Gott, explains why some galaxies in crowded environments are found gasping for fuel. During a major merger, the situation becomes even more extreme. The gravitational chaos violently stirs the intracluster medium, and it can also fling galaxies on high-speed trajectories through this newly disturbed, denser gas. The ram pressure acting on these galaxies is dramatically enhanced, leading to an efficient and rapid removal of their cold gas reservoirs. We see clear evidence of this in the nearby Virgo cluster, where many galaxies display truncated gas disks and long, faint tails of ionized hydrogen trailing behind them like cosmic exhaust, telling the story of their passage through the cluster's core. How does this loss of fuel impact the long-term evolution of a merged node? This environmental quenching is a primary reason why the central regions of mature clusters are dominated by passive red galaxies. Without the cold gas to form new, hot blue stars, these galaxies simply age, their stellar populations growing older and redder with time. Their brilliant fire is not violently extinguished by internal feedback, but is instead slowly suffocated by the very environment they call home. This faint, ghostly glow is the final echo of a cosmic demolition, enveloping the brilliant core of a massive galaxy. A vast and diffuse stellar halo shimmers with the light of countless exiled stars. These are the sole survivors of entire galaxies that were torn apart over billions of years, their identities erased, their stars scattered into a permanent, wandering cloud. Astronomer John Moustakas aptly calls this the archaeological record of a cluster's history, a fossilized imprint of its most violent encounters. While many processes contribute to this stellar haze, major mergers are the most effective liberators. The immense gravitational tides unleashed during these collisions do not just distort galaxies, they rip stars from their galactic homes entirely, flinging them out into the emptiness between galaxies. This creates an extensive, smooth halo of intracluster light, a faint luminosity that can account for a staggering fraction of the node's total stellar mass, often exceeding 10%. In clusters like Perseus, deep observations reveal spectacular, intricate streams of this ancient starlight, tracing the gravitational pathways of long-finished mergers like cosmic contrails. What secrets are locked within the specific patterns and colors of this faint light? The very smoothness of the halo tells a story of thorough mixing, the result of many mergers over immense timescales. More intriguingly, the metallicity of these stars, their chemical fingerprint, acts as a cosmic clock and a place of origin. Stars with higher metal content were likely stripped from the inner, more evolved regions of massive galaxies, while metal-poor stars hint at their birth in small, primordial dwarf galaxies. By mapping this faint stellar haze, astronomers can effectively rewind time, piecing together the sequence, the timing, and even the types of galaxies that built the node we see today. Yet capturing this archaeological record is one of astronomy's greatest technical challenges, requiring some of the most sensitive telescopes and longest exposures to see a glow millions of times fainter than the dark night sky itself. Amidst the visible chaos of colliding galaxies lies another, invisible force reshaping the drama. Galactic magnetic fields, faint threads woven through the cosmic void, become powerful actors during a merger. These fields are unimaginably weak by earthly standards, yet in the vastness of space they are crucial. As two galaxies intertwine, their turbulent flows of gas act like a cosmic dynamo. The immense compression and shear forces violently stretch, twist, and amplify these magnetic fields, strengthening them by orders of magnitude. Pioneering radio astronomer Rainer Beck has spent decades mapping these invisible structures, revealing how they trace the ghostly skeleton of a galaxy's shape. In systems like the Taffy galaxies, a stunning example of a recent collision, observations show a turbulent and amplified magnetic field stretched like a bridge of force between the two separating cores. This reconfigured magnetic web fundamentally alters the behavior of the entire system. The strengthened fields provide a form of cosmic pressure, influencing the collapse of giant gas clouds. They can both support a cloud against gravitational collapse, slightly suppressing star formation, or channel flows of material to help create denser, more massive stellar nurseries. Furthermore, these twisted magnetic fields act as conduits and traps for high-energy cosmic rays, particles accelerated to nearly the speed of light by supernova explosions. The fields guide these rays, preventing them from simply escaping into empty space, and instead allowing them to deposit their energy back into the gas, further heating it and influencing the feedback cycle. This intricate magneto-hydrodynamic interplay, where magnetic forces dance with gravity and fluid motion, adds a profound layer of complexity to our understanding of how a cosmic node evolves. It is a hidden dimension of physics that dictates not just where stars are born, but how the entire galactic ecosystem regulates its own turbulent growth. From the wreckage of galactic collisions, entirely new worlds can be born. Long, graceful tidal tails pulled from the hearts of merging galaxies, are not merely streams of scattered stars. Within these cosmic rivers, dense pockets of gas and stars can collapse under their own gravity, giving rise to a unique class of object, the tidal dwarf galaxy. Unlike the primordial galaxies that formed from the pristine gas of the early universe, these are second-generation systems built from the recycled debris of a cosmic crash. They are self-gravitating islands, pulling themselves together from the expelled material of their colossal parents. The renowned astronomer Pierre-Alain Duc has identified many such candidates nestled within the tangled webs of interacting systems, like the famous antennae galaxies. Their bright knots of intense light within the long tails are not just clusters of stars, but likely the brilliant cores of nascent tidal dwarf galaxies in the act of formation. This presents a fascinating puzzle because they form from gas and stars already stripped from the galactic disks. These newborn galaxies are born without the deep, invisible anchor of a dark matter halo. They are built from the visible, baryonic matter that makes up our familiar world, but they lack the dominant gravitational scaffolding that holds primordial galaxies together. This raises a profound question about their destiny. Can a galaxy without dark matter survive for billions of years in the harsh gravitational environment of a cosmic node? Their very existence offers a pristine laboratory. By studying tidal dwarf galaxies, astronomers can observe the process of gravitational collapse and star formation in an isolated environment, free from the complicating influence of dark matter. Their long-term fate, whether they are transient features destined to be reabsorbed or stable, long-lived satellites, will reveal fundamental truths about what it takes for a galaxy to endure. The superheated plasma that permeates the space between galaxies holds the majority of a node's normal matter. This intracluster medium, a searing ocean of multimillion-degree gas, glows not in visible light but in a brilliant, high-energy X-ray haze that reveals the violent history of the entire cluster. When two galaxy clusters collide, they do not pass through empty space, but through this incredibly hot, thin, yet substantial medium. The merger sends titanic shockwaves rippling through the plasma, like sonic booms on a cosmic scale, compressing and heating the gas to even more extreme temperatures. These immense disturbances are etched directly into the X-ray morphology of the cluster, appearing as sharp edges, swirling turbulence, and dramatic variations in temperature. A breathtaking example of this is the Bullet Cluster, where a smaller cluster has punched right through the heart of a larger one. The X-ray observations show a clear, bullet-shaped shock front plowing through the intracluster medium, a permanent scar of this high-speed collision. This injection of colossal energy directly into the plasma is more than just a spectacular sight. It is a critical piece of solving a long-standing astrophysical puzzle. For decades, astronomers were perplexed by what they called the cooling flow problem. The simple physics suggested that this dense, hot gas at the center of clusters should rapidly lose its energy, cooling down and collapsing to form a deluge of new stars at a rate that would create thousands of new suns every year. Yet observations showed this was not happening. The star formation was strangely suppressed. The answer lies in the very violence of these mergers. The immense shock waves and turbulence they generate act like a cosmic stirring spoon, pumping energy back into the cooling gas and preventing it from settling down to form new stars. This feedback, where the chaos of a collision regulates the future growth of the node, is a fundamental balancing act that prevents clusters from burning through their fuel too quickly. Without these periodic, violent injections of energy, the cosmic web would look profoundly different, its nodes shining with a far more intense, youthful blue light. These cosmic shock waves are sonic booms of almost unimaginable scale. When two subclusters, each containing hundreds of galaxies, slam together at thousands of kilometers per second. Their motion is supersonic relative to the thin, hot plasma that fills the space between them. This collision does not happen in silence, but generates vast, expanding fronts of compressed energy that race outward through the intracluster medium. These are the merger shocks, some of the most powerful events to ripple through the universe since its fiery beginning. The energy they release is staggering, violently heating the already superheated gas and acting as natural particle accelerators on a cosmic scale. Within these turbulent fronts, existing populations of cosmic rays, high-energy particles left over from supernova, are caught in the shock's grip and re-accelerated to even more incredible energies. This process creates a faint, diffuse glow detectable at radio wavelengths, a phenomenon astronomers call a radio relic. For researchers like Reinout van Wieren, these relics are not just energetic curiosities, they are forensic evidence. Hunting for these faint signals across the sky allows him to trace the outlines of colossal collisions that occurred billions of years ago, long after the visible galaxies have finished their merger dance. A prime example is the object nicknamed the Sausage Relic, found in cluster Caesar J2, 124 2.8 plus 5301. This gigantic, arc-like structure of radio emission is a direct imprint of a powerful shock wave that is still propagating through the cluster. The very shape of this relic is a data-rich snapshot of the ancient impact. Its remarkably sharp and narrow edge indicates the precise location of the shock front itself, while its spectrum, the way its radio emission changes with frequency, acts as a cosmic speedometer. By analyzing this spectrum, astronomers can calculate the velocity of the shock wave, which in turn reveals the ferocious speed at which the original subclusters collided. The geometry of the arc, a vast, smooth curve, tells a story about the angle and the symmetry of that long-ago encounter. These ghostly radio structures are therefore fossil imprints, permanent records etched into the fabric of space that allow us to reconstruct the dynamics of a cosmic crash with stunning precision, long after the visible fireworks have faded into darkness. A stark division cuts across the cosmos, a great cosmic schism separating two families of galaxies. On one side lies the vibrant blue cloud, a population of spiral galaxies alive with the hot, brilliant light of newborn stars. On the other rests the red sequence, a quiet congregation of elliptical galaxies, their glow dominated by the cooler, older stars that remain after star formation has ceased. This color bimodality is not a static picture, it is a dynamic spectrum of galactic life and death, and its primary architect is the violent process of galactic merger. The work of astronomers like Michael Balog has been pivotal in mapping this transition, revealing how major collisions act as a powerful conveyor belt, moving galaxies from the blue cloud to the red sequence. The mechanism is devastatingly effective. A merger consumes the cold gas fuel in a final, furious starburst, while the ensuing feedback from the central black hole heats and expels any remaining reserves. Simultaneously, the gravitational chaos transforms the galaxy's structure, stabilizing it into a smooth, passive elliptical system no longer capable of forming new stars. Without the short-lived, brilliant blue stars, the galaxy's overall color steadily reddens over hundreds of millions of years. This is the ultimate fate of many galaxies funneled into the dense nodes of the cosmic web. The demographics of a node, the simple ratio of red galaxies to blue ones, therefore becomes a profound historical record. A node dominated by a strong red sequence is an old, mature system, one that experienced its last major merger events long ago, leaving its constituent galaxies quiescent and red. A node with a more mixed population, however, tells a story of recent assembly, where the fires of creation have only recently been extinguished. By taking a cosmic census of galaxy colors, we can effectively read the assembly history of the entire universe, tracing the epoch when the most massive nodes completed their construction and the great transition from blue to red swept across the cosmos. A galaxy's spin is a fragile thing. That graceful rotation, a product of billions of years of quiet evolution, is a primary casualty in the violent chaos of a merger. The intricate gravitational dance between the two colliding systems acts as a cosmic engine for redistributing angular momentum, the fundamental property of spin. This is not a simple transfer but a complex scattering. The orderly rotation of the stellar disks and their gas is violently disrupted, its energy siphoned away. A significant portion of this lost spin is transferred outward, absorbed by the vast, encompassing dark matter halo, causing it to swell and change its own subtle rotation. Another fraction is converted into the orbital energy of the few surviving satellite galaxies, or is carried away entirely by the long tidal tails of stars and gas flung into the void. Pioneering theoretical work by scientists like Giulio Navarro has traced how dark matter halos themselves acquire their spin through the cumulative tidal torques and mergers experienced over their entire history. This exchange is a pivotal part of the merger process, often acting as a cosmic pump. The same torques that drain spin from the outer regions of the galaxy can also drive incredible inflows of gas violently inward, directly fueling the central starburst and the supermassive black hole. This is why the brilliant, compact cores of some merger remnants are found to be spinning rapidly, even as the main body of the galaxy has lost its organized rotation. We see this stunning dichotomy captured in the aftermath of a merger known as NGC 7252, the Atoms for Peace galaxy. Observations reveal a small, rapidly rotating disk of gas and stars nestled at its very heart, a whirling dynamo that formed from gas funneled to the center during the collision. Yet this central pinwheel is embedded within a much larger, slowly rotating, and puffed-up stellar body that shows almost no net spin, a testament to the randomization of the original galactic disks. This fundamental loss of spin has permanent consequences for the resulting galaxy. A system with little organized rotation is far more stable against collapsing back into a disk structure. It is this randomization of angular momentum that helps lock the galaxy into its new, stable, elliptical form, preventing it from ever re-establishing the delicate balance of a spiral. How does this fundamental change affect the stability of the node's central galaxy? The final angular momentum budget becomes a lasting legacy of the collision, a hidden fingerprint that determines the long-term structure and destiny of the giant elliptical that now anchors the cosmic node. A galaxy can be a ghost. Some of the most perplexing inhabitants of merged cosmic nodes are the ultra-diffuse galaxies, vast, wispy structures as wide as the Milky Way, yet containing only a tiny fraction of its stars. Their faint glow is so dispersed that they barely register against the blackness of space, earning them their spectral name. The formation of these cosmic phantoms is a deep puzzle. One compelling theory suggests they are failed tidal dwarfs, born from the same collisional debris that creates their more robust cousins, but which somehow failed to gather enough gas to ignite a significant firestorm of stars. Another possibility is that they are ordinary dwarf galaxies that underwent a dramatic transformation, their gas violently stripped away by the intense ram pressure of a high-speed plunge through a merging cluster. Astronomer Pieter van Dokkum and his team have been pioneers in hunting these elusive objects, using innovative telescopes to tease their faint light from the darkness. Their very existence defies simple expectations. With such low densities and feeble gravity, they should be incredibly fragile, easily torn apart by the fierce tidal forces within a dense node. Yet against all odds, many of them endure. This paradox finds its ultimate expression in Dragonfly 44, a famous ultra-diffuse galaxy in the Coma cluster. Despite its ghostly appearance, measurements of the motions of its few stars reveal a startling truth. Its mass is immense, dominated by a colossal halo of dark matter that holds the fragile stellar cloud together. This discovery challenges the idea that all ultra-diffuse galaxies are simple, failed systems, forcing astronomers to consider a wider range of violent birth stories. What do these enigmatic, translucent giants tell us about the extreme physics of cluster assembly? They are cosmic outliers, the unexpected and puzzling results of a node's most violent encounters, challenging our very definitions of what a galaxy can be. A cosmic lens of unimaginable power warps the very fabric of spacetime around a massive node. This phenomenon, known as strong gravitational lensing, transforms the node into a natural telescope, magnifying and distorting the faint light from galaxies that lie billions of light years behind it. The resulting images are spectacular cosmic mirages, where a single background galaxy can appear as multiple stretched arcs of light, a direct consequence of the node's total mass bending the path of light itself. For astronomers like Jean-Paul Nabe, these distorted images are not just beautiful curiosities, they are precise forensic tools. By meticulously mapping the intricate patterns of these arcs, they can chart the invisible distribution of dark matter that constitutes the vast majority of the node's gravitational anchor. The lensing strength is a direct measure of this total weight, but what happens when that weight is thrown into violent motion during a major merger? The clean, symmetric lensing pattern of a relaxed cluster shatters. As the dark matter halos and the hot gas slam together, the mass distribution becomes profoundly asymmetric and clumpy. This distortion in the invisible scaffolding creates a corresponding distortion in the lensed images. Multiple new images of the same background galaxy can suddenly appear, and the graceful arcs can twist into complex, knotted shapes. The renowned cluster Abell 370 offers a stunning example. Its collection of giant blue-lensed arcs, including one whimsically nicknamed the Dragon, betraying a mass distribution that is far from smooth, strongly suggesting a past merger that has left the dark matter halo permanently disturbed. This leads to a profound possibility. If we could observe a node frequently enough over years or decades, could we actually witness the lensing pattern change in real time? The subtle shifts in the positions and brightness of these multiple images, known as time-variable lensing, would provide a direct, dynamic view of the dark matter rearranging itself. This would offer a unique, weight-based view of the merger's progression, allowing us to see the cosmic node not as a static monument, but as a living, evolving structure, its gravitational influence shifting with the rhythm of collision. The final, ferocious dance of two supermassive black holes sends tremors through the cosmos itself. As these colossal objects, each weighing millions or even billions of times the mass of our Sun, spiral toward their inevitable union, they do not orbit through empty space. They warp the very fabric of spacetime, generating ripples that propagate outward at the speed of light. These are gravitational waves, the direct echo of the most powerful collisions since the Big Bang. While observatories like LIGO have successfully listened to the higher-pitched chirps from merging stellar mass black holes, the deep, bass notes of supermassive binaries require an entirely different kind of ear. Their waves oscillate with periods of years, demanding a detector of staggering scale, one that must be built in the pristine quiet of space. This is the mission of the future LISA Observatory, a fleet of 3 spacecraft that will form a gravitational wave antenna millions of kilometers across. Astronomer Alberto Cesana and his colleagues are at the forefront of this new field, using sophisticated simulations to predict the precise hum and chirp this cosmic symphony will produce. The journey to this final merger is a long and complex one. After their host galaxies collide, the two black holes are initially left far apart, separated by thousands of light years. They are slowly drawn together through a process called dynamical friction, where their immense gravity plows through the surrounding sea of stars and gas, creating a gravitational wake that saps their orbital energy and pulls them inexorably inward. Eventually, they form a tight binary system, locked in a final, ever-tightening orbit. It is in this last, furious in-spiral that they become a potent source of gravitational waves, radiating away their remaining orbital energy in a rising crescendo. The final merger is an event of almost incomprehensible power, briefly outshining the combined light of every star in the observable universe. But what is the ultimate prize of listening for these cosmic tremors? The detection of a background hum, a continuous sea of low-frequency waves from all the supermassive black hole mergers happening across the cosmos, would open a completely new window onto the evolution of the large-scale structure. This gravitational wave background is the cumulative record of every major node assembly throughout cosmic time. By decoding its subtle statistical properties, we could read the entire history of how the cosmic web was built, from the first giant collisions to the mature nodes we see today. It would be the final, definitive proof of the hierarchical model, allowing us to hear the universe's most violent and creative moments unfold. The violence of a galactic merger does not end at the node's edge. Ripples from this cosmic collision travel far along the delicate filaments of the Great Web, influencing the destiny of galaxies yet to form. Between these vast structures lies the intergalactic medium, an incredibly thin and pristine gas that is the final frontier, the raw material for all future cosmic construction. When a node erupts in the firestorm of a merger, the resulting outflows act like a cosmic pollution event. Powerful winds, driven by the combined fury of countless supernovae and the intense radiation from an awakened black hole, blast outwards. They carry with them a cargo of heavy elements, freshly forged in the stellar furnaces of the collision, and inject tremendous energy into the surrounding void. We can see a local, smaller-scale version of this process in the nearby starburst galaxy M82, where a galactic superwind is visibly ejecting a fountain of hot, metal-rich gas far out into intergalactic space. This large-scale circulation of matter and energy is a form of cosmic feedback, a process theorists like Rommel Dave have shown is essential for regulating the growth of galaxies. By preheating the diffuse gas in the filaments, these outflows raise its temperature, making it more difficult for that gas to cool down, collapse, and eventually fall into a waiting galaxy. This feedback loop creates a profound connection between the most violent events in the densest nodes and the most quiet, empty regions of the cosmos. It means that the death throes of one generation of galaxies, their brilliant firestorm of creation, directly shapes the potential for life in the next. The very elements that will one day form planets and living worlds are first scattered into the void by these colossal explosions, seeding the cosmic web with the ingredients for a more complex future. The dramatic collisions of galactic titans are not the only story. A quieter, more continuous form of assembly is always at work, a steady drizzle of minor mergers that constantly stirs the cosmic node. While a major merger is a violent revolution that remakes a galaxy's core identity, a minor merger is more of a persistent renovation. This process involves a large galaxy, like our own Milky Way, gradually consuming a much smaller satellite, one perhaps only 1/100th of its mass. These events are far more common than their colossal counterparts, and their cumulative effect over billions of years is a fundamental driver of galactic evolution. They are the constant, gentle rain that, drop by drop, helps to fill the ocean of a galaxy's halo. Astronomer David Martinez Delgado and his team have become cosmic archaeologists of these events. They use powerful telescopes to hunt for the faint, telltale signs of these ancient meals, the delicate tidal streams of stars that wrap around host galaxies like ghostly ribbons. These stellar rivers are the final, dissolving signatures of dwarf galaxies that were torn apart by relentless tidal forces, their stars slowly being assimilated into the larger galaxy's extended halo. We have a front-row seat to this very process in our own cosmic neighborhood. The Milky Way is currently in the act of digesting the Sagittarius dwarf spheroidal galaxy. This small satellite has been stretched into a long, shimmering stream of stars that encircles our entire galaxy, a beautiful and ongoing testament to the process of hierarchical growth. The impact of a single minor merger is subtle but profound. It does not have the raw power to completely destroy a grand spiral disk the way a major collision does. Instead, its gravitational influence acts like a gentle stirring spoon, perturbing the orderly orbits of stars in the thin disk and causing it to puff up and thicken over time. It can also funnel small amounts of fresh, cold gas inward, triggering localized and modest bursts of new star formation, a gentle refresh rather than a raging firestorm. So how does this slow and steady accumulation compare to the sudden, violent influx of a major merger? The difference lies in the pathway of growth. A major merger is a singular, catastrophic event that rapidly forges a new type of galaxy, an elliptical, from the wreckage of two spirals. It is a dramatic, top-down transformation. In contrast, the cumulative effect of countless minor mergers is a patient, bottom-up assembly. It steadily increases the mass and size of the central dominant galaxy in a node, building up its stellar halo star by star and subtly altering its morphology over eons without ever completely erasing its fundamental disk structure. This continuous drizzle ensures that even in the relative quiet between cosmic crashes, the nodes of the Great Web are never truly at rest, but are always being slowly and meticulously reshaped. This shift in galactic color tells a profound story of cosmic aging. Look deep into the universe, to the farthest reaches where light has traveled for billions of years to reach us, and you will find galaxy clusters that appear strangely blue and vibrant. Peer at a similar cluster closer to home, in our contemporary cosmic neighborhood, and you will mostly see a quiet, red collection of galaxies. This dramatic transformation is known as the Butcher-Oemler Effect, a discovery by astronomers Harvey Butcher and Augustus Oemler that gives us a time-lapse view of the universe's evolution. The effect reveals a clear pattern. The further back in time we look, the higher the fraction of blue, star-forming galaxies we find within the dense nodes of the cosmic web. What we are seeing is a universe in its youth when cluster nodes were chaotic construction sites, not the quiet retirement homes they often are today. In that distant past, galaxies were still gas-rich, and their close quarters led to frequent, violent interactions and mergers. These collisions ignited the brilliant blue fire of starbursts, painting the clusters with the light of newborn suns. A stunning modern confirmation of this comes from clusters like CLJ 1001 plus 0220, observed at a tremendous distance. Its core is not dominated by red giants, but is instead teeming with a significant population of blue, active galaxies caught in the act of intense assembly. This tells us that the peak era for building these massive nodes was a turbulent and prolific time, a cosmic golden age of violent creation. As the universe expanded and aged, the raw material for new galaxies was consumed. The rate of major gas-rich mergers decreased, and the processes we have explored, from ram pressure stripping to black hole feedback, slowly quenched the remaining star formation. The blue stars burned out, leaving behind the older, redder populations that define mature clusters today. The Butcher-Oemler Effect is therefore more than a simple color change. It is the fading echo of the universe's most violent and creative period, a direct observation of the cosmic web settling into its present, more tranquil state. Even the faint afterglow of the Big Bang itself is not safe from the violence of a merging node. This ancient light, the cosmic microwave background, has traveled for over 13 billion years to reach us, and on its long journey, it must pass through the superheated plasma of galaxy clusters. When it does, a subtle but profound interaction occurs. The high-energy electrons in the intracluster medium give the passing photons a tiny energy boost, a process known as the Sunyaev-Zeldovich Effect. The result is a faint, cool shadow imprinted on the microwave sky, a silhouette of the cluster's hot gas. This shadow is not a simple dark spot, but a precise measurement of the total thermal energy contained within the entire node. When a merger sends shock waves through the intracluster gas, violently heating it to even more extreme temperatures, this shadow deepens and distorts. The integrated Sunyaev-Zeldovich signal becomes a direct gauge of the immense energy injected into the system by the collision. This makes the effect an incredibly powerful tool for cosmologists, as it allows them to discover and study clusters completely independently of their distance from us. While a cluster's visible light fades and reddens with cosmic expansion, its Sunyaev-Zeldovich shadow remains just as distinct, a distance-free beacon in the microwave sky. Pioneering experiments like the Atacama Cosmology Telescope scan the heavens, not in visible light, but in microwaves, meticulously mapping these subtle imprints to build vast catalogs of clusters across cosmic time. The real power of this technique shines when we examine a known merging cluster, like the colossal system nicknamed El Gordo. This distant titan, a pair of subclusters caught in a high-speed collision, shows a dramatically disturbed and amplified Sunyaev-Zeldovich signal. The map does not show a single, smooth shadow, but a complex, elongated shape that traces the furious interaction of the two gas clouds. This provides a unique, energy-based view of the merger's dynamics, complementing the pictures we get from X-rays and gravitational lensing. How can these microwave maps help us trace the evolution of the cosmic web? By surveying huge volumes of the universe for these distinct shadows, astronomers can compile a cosmic census of nodes and identify which ones are currently undergoing violent assembly. This redshift-independent tool allows us to track the growth of the largest structures in the universe from its youth to the present day, offering a direct test of our models for how the great cosmic web was woven together. These smallest galaxies face the greatest peril within a crowded cosmic node. A dwarf galaxy, a fragile collection of a few billion stars, drifts into the gravitational metropolis, and the environment it enters is ruthlessly efficient at reshaping it. The relentless tidal forces from massive neighbors act like a gravitational rack, slowly pulling and stretching the dwarf, disrupting its delicate structure. At the same time, the pressure from the superheated intracluster medium acts like a cosmic sandblaster, violently stripping away its precious reservoirs of cold gas. This 1-2 punch of tidal harassment and ram pressure stripping effectively suffocates the dwarf, halting any future star formation in a process astronomers call environmental quenching. The work of researchers like Elena de Ongea has been crucial in simulating these subtle but destructive interactions, revealing how a once vibrant dwarf can be transformed into a faint, quiescent spheroidal system. We see this story written across the satellite galaxies of our nearest giant neighbor, the Andromeda Galaxy. Its halo is populated by numerous dwarf spheroidals, quiet and gas-poor, their star forming years long behind them, each one a testament to the transformative power of the node. This leads to a profound diagnostic tool. The very population of dwarf galaxies surviving in a node serves as a sensitive fossil record of the node's own violent past. A node with a rich and diverse population of dwarfs, including some that have retained their gas, likely experienced its last major merger more recently, its gravitational turbulence not yet having had time to fully process these small systems. Conversely, a node that is almost completely devoid of primordial dwarfs, or one where every dwarf is a red and dead spheroidal, speaks of an ancient and dynamically mature environment, one that has spent billions of years efficiently quenching its smallest inhabitants. The survival and specific properties of these countless tiny galaxies therefore tell a detailed story of persistent gravitational harassment over cosmic time, a slow and steady pressure that is just as transformative as the sudden violence of a major collision. These vast rivers of motion are the universe's ultimate destiny map. The cosmic web is not a frozen sculpture but a dynamic highway, with entire galaxies and galaxy clusters flowing like traffic along its dark matter filaments. This grand motion, known as bulk flow, is a gravitational river on the largest scales imaginable, pulling countless nodes toward regions of even greater mass and density. These flows are not random, they are the direct consequence of immense gravitational shadows cast by superclusters, the next level up in the cosmic hierarchy. The movement is slow and stately, measured over hundreds of millions of years, but its implications are profound. It is this large-scale streaming that gently nudges separate nodes closer together over cosmic time, setting them on a collision course for the future cluster mergers that will forge the next generation of supernodes. Astronomers like Dale Kosofsky meticulously measure these subtle motions, using the collective movement of thousands of galaxies as a tracer. Their data provides a unique map of the invisible mass distribution, revealing the hidden gravitational mountains and valleys that dictate the universe's long-term evolution. We are part of this flow ourselves, our own local group of galaxies, including the Milky Way and Andromeda, is caught in this cosmic current, pulled toward the mysterious gravitational center known as the Great Attractor. This region, hidden behind the dust of our own galaxy's central plane, exerts a pull on thousands of galaxies in our vicinity. So how do these flows determine which nodes are destined to merge? The answer lies in the initial conditions of the universe itself. The subtle variations in density from the Big Bang created a specific gravitational landscape, and bulk flows are simply the universe following these contours, sliding downhill into the deepest potential wells. The nodes that end up in the same gravitational watershed are the ones that will eventually be drawn together, their individual merger histories culminating in a final, colossal union. This grand perspective places the violent evolution of every single node within the context of the universe's overall expansion and structure formation, revealing a cosmic destiny written not in the stars, but in the silent, relentless pull of gravity itself. This brilliant violence is its own greatest limitation. The very starbursts and active galactic nuclei that a galactic merger unleashes generate so much energy that they ultimately shut down the process that created them. It is a cosmic balancing act of remarkable precision, a form of self-regulation known as feedback. This process directly couples the furious physics of individual stars and black holes to the grand evolution of an entire galaxy, and by extension, the node it anchors. The immense radiation and powerful winds from a starburst, combined with the ferocious output from a feasting black hole, blast through the surrounding galaxy. This energy does not simply vanish, it violently heats the vast clouds of cool gas, the raw fuel for new stars. By superheating this reservoir, feedback prevents the gas from cooling, collapsing, and forming new stellar generations. It is the universe's primary mechanism for preventing a galaxy from growing indefinitely, ensuring that no single structure becomes overwhelmingly massive. Sophisticated theoretical models like the Eagle simulation vividly illustrate this process. They show how the energy injected by feedback can drive colossal galactic winds, powerful enough to eject significant amounts of gas entirely from the galaxy's gravitational grasp. This effectively quenches star formation, putting a definitive ceiling on the galaxy's growth. A stunning real-world example of this is the Phoenix Cluster, a massive node where the central black hole is engaged in a titanic struggle. It is blowing enormous bubbles of energetic particles directly into the superheated plasma that surrounds it, like a cosmic engine churning the atmosphere to prevent it from settling. This self-regulating mechanism elegantly solves one of cosmology's enduring puzzles, establishing a natural upper mass scale for the most massive galaxies and nodes. Without this built-in cosmic thermostat, the universe would be a very different place, dominated by impossibly large and brilliant galaxies that defy our understanding of gravity and structure. Feedback is the quiet governor that maintains order amidst the chaos, ensuring the cosmic web evolves according to a set of subtle, universal rules. Our own galactic home is not an island, but a participant in this grand cosmic dance. The Milky Way and the Andromeda Galaxy, along with dozens of smaller companions, form a small but significant node known as the local group, and its ultimate fate is a slow-motion collision already in progress. Andromeda is hurtling toward us at a velocity of over 100,000 kilometers per hour, set to meet our galaxy in a direct encounter roughly 4 billion years from now. This is not a prediction of destruction, but a forecast of creation, a future where our two great spirals will coalesce into a single, giant elliptical galaxy that astronomers have nicknamed Milkdromeda. The pioneering work of scientists like Roland van der Merwe, using precise data from the Hubble Space Telescope, has given us a stunningly detailed timeline of this event. The first close pass will be a gravitational spectacle, a near miss that pulls both galaxies into long, streaming tails of stars, dramatically warping their familiar shapes beyond recognition. They will then swing back, their cores merging in a final, decisive union that will fundamentally reconfigure our entire local node. This process will not be a gentle one. The orderly spiral disk of the Milky Way will be scrambled into a chaotic, swelling sphere. Vast clouds of gas will be compressed, igniting a brilliant starburst that will forge new generations of stars at a ferocious rate. This incoming fuel will also plunge toward the center, feeding the merged supermassive black hole and likely awakening it as a brilliant active galactic nucleus, a beacon visible across intergalactic space. The entire structure of our local web will be rewritten. Smaller galaxies like the Triangulum Galaxy will be drawn into the chaos, likely consumed or stripped apart, their stars added to the growing halo of the new galactic titan. For any potential future civilization witnessing this event from within, the night sky would be utterly transformed. The familiar band of the Milky Way would be gone, replaced by a dazzling, chaotic sky filled with the fiery glow of new star clusters and the distorted shapes of the merging galaxies. The serene darkness would be punctuated by the brilliant light of the active galactic core, outshining all other celestial objects. This brings the entire epic story of node evolution directly to our celestial doorstep, a future chapter written in the motions of the stars above us, reminding us that the cosmos is a place of perpetual, majestic change. Peering deep into the cosmic past requires a time machine, And our most powerful telescopes are precisely that. By capturing light that has traveled for billions of years, instruments like the Hubble and now the James Webb Space Telescope allow us to witness the universe in its youth during the era when the cosmic nodes were under furious construction. Astronomer Garth Illingworth's work with the Hubble Deep Field revealed a cosmos starkly different from our own, one teeming with irregular, clumpy galaxies caught in the act of frequent collisions. This distant sky is not dominated by the serene spirals and smooth ellipticals we see nearby, but is instead a chaotic construction site, a testament to a time when mergers were the dominant force of change. These observations are not just snapshots, they are crucial data points that test the very foundations of our models. How quickly were these massive nodes assembled? The evidence points to a rapid and efficient process. Studies of the most distant, and therefore youngest, massive galaxies show that their dense cores formed remarkably early. The outer regions, the extensive halos of stars and dark matter, were then built up over subsequent billions of years through a steady rain of smaller mergers. This inside-out formation scenario is a key prediction of hierarchical structure formation, and seeing it confirmed across cosmic time validates our understanding of how gravity built the universe from the bottom up. The Hubble Ultra-Deep Field provides a stunning census of this turbulent epoch. Within its tiny patch of sky, countless galaxies appear distorted, stretched, and linked by bridges of light, each one a frozen moment in a slow-motion dance of destruction and creation. This is the direct evidence of the peak merger era, the violent period when the blue cloud of star-forming galaxies began its great transition to the red sequence. By counting these interactions and measuring their properties at different look-back times, astronomers can construct a precise timeline of node evolution. They can determine when the most massive clusters finished their primary assembly and when the great quenching of star formation began to sweep across the universe. Each deep field image is therefore more than a collection of beautiful objects. It is a historical document, a chapter in the biography of the cosmic web, allowing us to watch the nodes of the great web being forged in the fires of their own violent youth. The brilliant, chaotic history of node assembly is but a single, vibrant chapter in a much longer and darker cosmic story. Trillions of years from now, the accelerating expansion driven by dark energy will fundamentally rewrite the destiny of the great web. For a time, gravity will continue its work, pulling nearby clusters together into ever more massive superclusters. But this is a final, fleeting consolidation. Eventually, the relentless push of dark energy will overcome even the strongest gravitational bonds. The delicate filaments connecting the nodes will stretch, thin, and finally snap. Each colossal node, the product of countless ancient mergers, will become an isolated island universe, adrift in an ever-expanding and rapidly emptying void. Theorist Fred Adams, in his profound exploration of deep time titled The 5 Ages of the Universe, charted these vast epochs, describing a future where the universe transitions from its current stelliferous era, dominated by stars, into a final, dark age. The legacy of every dynamic merger we have explored, every starburst and quenched galaxy, is that it forged these final, stable structures. They will become the last bastions of light and complex structure in a cosmos growing cold and dark. Within these isolated nodes, star formation will have long since ceased. The last red dwarf stars will flicker out, and only the faint warmth of stellar remnants will remain. So what is the ultimate meaning of all that violent, creative collision? It is the universe's way of building its most enduring monuments. In a cosmos destined for silence and isolation, the merged nodes stand as the final, grand testament to an era of gravity and light, the permanent record of a time when the universe was alive, dynamic, and fiercely creative. Our journey reveals a universe built by collisions, where the fiery chaos of merging galaxies forges the very architecture of reality. These events are not merely destructive, they are the fundamental engines of cosmic change, sculpting the forms of galaxies, seeding the void with the elements for life, and governing the growth of the largest structures we can see. The invisible hand of dark matter directs this grand performance, while powerful feedback loops ensure that no single structure grows without limit, maintaining a delicate balance across the eons. The great astronomer Carl Sagan once reflected that somewhere, something incredible is waiting to be known. That search continues today, as each new observation of these cosmic nodes peels back another layer of our universe's profound history and points toward its ultimate destiny. This understanding of events unfolding over incomprehensible distances and timescales connects deeply to our own story. The atoms that form our world, our planet, and ourselves were forged in the hearts of ancient stars and scattered across the galaxy by these very collisions. We are not just observers of this cosmic drama, we are a product of it. If this exploration of the universe's great mysteries has captivated you, please subscribe for more journeys into the unknown and share your own thoughts on galactic mergers in the comments below.